Hello everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to show you how you can find things that are out of place. It's been a long journey so far. I think this is around video 50 in this series. We've done a lot of theoretical stuff recently, looking at the big picture of how disks are laid out, and today I'm going to show you how you can get some of the fruits of that knowledge, how you can apply your understanding of how things should be in order to find out if things are kind of out of place. So let's get started. I'm going to start by mounting my image. So I will use my mount image pi, and my image is going to be media, Phil, Toshiba, disk images, 2015-39 IMG. Go ahead and mount that. And you can see it brought up this guy. If I do a quick check with mount, I will see that yes, in fact, this was mounted as read-only, which is important, of course. So I'll go on over to where this was mounted. And let's start with the most important things. So if I'm going to break into your system, compromise your system, and do something bad, I will probably try to alter things in the bin directory and the sbin directory. There are other places that things might get modified, but this is a good first place to look. So in order to see if things have been changed, I can very easily look at what inodes were used for certain files. Now remember, the inode is the collector of the metadata. It has everything about the file except its name. We'll talk about how that's stored exactly in a future video. But for now, we know that the inode is sort of the king, and it's one of the most important pieces in this whole picture. So if I do an ls on my bin directory, and if I just do the normal ls, it will give me kind of standard information. And of course, you probably are familiar with the A flag to show everything. So I will go ahead and say A, please show me hidden files, L for a long listing. And this might be a new flag for you. It's the I flag for please show me the inodes. So I can say ls-ali, if that helps you remember it, for bin. And I also want to sort it by the inode number. So I will pipe this to sort-n for numeric sorting. And I will get something kind of like this. Now in this case, I don't see a bunch of non-sequential inodes until I get here. And check this out. So I have a bunch of sequential inodes, which makes sense. When the operating system was installed and all of this was laid down, it was just file after file after file. And suddenly, what do I find here but a big jump? I go from 549 to 7,076. So that's a huge jump, and that indicates that these were added much later. Now in this case, we didn't have a very sophisticated attacker. This attacker did not change these timestamps, which is very easy to do. There are different tools out there to backdate the files so they don't look out of place. Of course, these also have some suspicious names. So that's another clue there. I mean, they could have done certain things to hide this a little bit better, but they didn't. Let me do the same thing on my sbin directory. And here I see that there's nothing strange. It's all sequential, even to the very bottom. So I feel better about that. All right, another quick thing that you can do. You can also do an ls and sort your files by size. So I can do an ls dash ali, and I'm also going to add a capital R for recursive in case there's any subdirectories. Dash dash sort equals size, and I'll run this on bin. And to make my life easy, I'm going to pipe this to more. All right, so what do we notice? Here's what we notice. I have BusyBox, which is pretty large, and then I have Bash, which is also kind of large-ish. And what comes next? Well, this is very suspicious. I have false, which the only job of false is to just return false. And yet, this program is very large and is in fact the exact same size as Bash and has a date that it was modified around the time of this compromise. So again, this user was not extremely sophisticated and he didn't change the timestamps. But even if he had, we would have found him out because of this thing. Now, if I continue, you'll see there is a function called true that is very similar to false. And the function called true is going to be much smaller. Once again, I do see references to my reverse shell. Somewhere in here is my true function. I just missed it. So I'm going to just do this. So that is much smaller, 27K instead of over 102. So that's another simple thing that you can do. And of course, you want to do the same thing on sbin. So I will run my ls-ali-r, and I will sort on size for sbin, also pipe that to more. And I see biggest thing there, WPA supplicant, DH client, and nothing else looks terribly out of place in terms of the size for different items. I can also sort by time. You know, we already created a timeline in some earlier videos, but if you wanted to sort by time, you can do the ls command where the sort is not size, but the sort equals time. And that will show you the most recent items. And you can see that, at least according to the timestamps, there's nothing terribly recent in sbin. And if I do the same thing for bin, boom, right away, since he didn't modify the timestamps, I can see that these were changed. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, I'm going to show you a very simple shell script that you can use to identify some out-of-place inodes. In a previous video, we talked about how if someone puts something in one of your bin directories or sbin, you might have a sophisticated attacker that fixes the timestamps, but they might have an issue that you can still use to discover their activities because the inodes used for those new files will probably not be sequential with all the other inodes when the system was installed and everything was laid down. So this is just a simple script that you can use to make it a little bit easier than just running the ls command that I showed you earlier. So here's our script. We start out with shebang bin bash. I define a little usage function, and it says run this script and give me a path. I will give you a printout of files in that directory with their inodes, and I will also tell you if there are any gaps in the inodes. So here I check and see if you gave me less than one argument. Then I will yell at you and I will give you the usage statement. And here's the main script. So the first thing I do right here is I output to a temp file. And why do I do it this way? This is a little bit more efficient way to go. So I run my ollie. We talked about that. All files, long entries, inode information, capital R for recursive, in case there are anything in subdirectories. $1 is the parameter you passed in, and I sort it numerically, and I put it to this temporary file. I then declare a couple of things. I have found first inode. I set that equal to false, and I declare an integer value. That's what this means here. Declare -i called start inode. These are used for getting rid of some of the lines at the start of this file. So when you sort it numerically, you will probably have a line or two at the top that are not actually files. They will say something like ls/bin:, for example. So those you don't want. So here I read in the file line by line, and if you go down a bit, you will see this is a construct that you can use. I say while read line do, and down here at the done, I have less than and then my file name. So what this does is it processes this file that is given by temp ls, and I go through it line by line, and each line gives me one iteration through this loop. So here I'm dealing with those start lines, and I say if found first inode equals false. So I haven't found a legit line yet, so I echo the line out. I pipe that to word count -w, which says, please just give me number of words. Otherwise, it'll give me characters, words, and lines. I don't want that. I just want the one thing. This is in backticks, which causes this to be executed. And then that result is stored in double quotes. So it's a string. And I say if that is greater than 6. And why greater than 6? If you look at the output from this ls command, you will have at least 7 columns of output if it represents a file. So that tells me I've gotten to the start, semicolon, then, and what do? All right, I say that my starting inode number is, and let's break this one down. It's a little bit complicated. I echo the line and I pipe it to awk. In my awk program, if you will, says please print the first word, which should be the inode number. This is inside of $, followed by parentheses, and that takes all of this and turns it into a signal argument, which is passed to expression. That means please evaluate this expression and return the result. So this is in backticks, which causes that result to be stored in my integer. Again, I declared this as an integer up here, start inode. And you'll see why I needed to declare that as an integer here in a little bit. And then I set found first inode to true, and then I continue. So here, I'm going to echo out the line, and again, I pipe it to awk, and I print the first word, and that's Q. All right, so that's my current inode. And I say, if my starting inode is less than Q, then I'm going to print out a warning. And what I've done here is I'm using escape commands to print it in different colors. And we'll see the output of this in a bit. So if it's drastically different, in other words, I skipped more than a couple of inodes, I'm going to print it out in red. I'm going to give you a message saying out of sequence, inode detected. I expected this and I got something else. If it's just a couple, I print it out in yellow instead. If I have the situation, I reset the starting inode using the same construct I used earlier with expr and echoing the line to awk. Here's the end of my if statement. I then echo the line. So regardless of whether or not there's a missing inode, I always echo the line. Then I increment the start inode. And this is why I had to declare this as an integer. So this is a construct in bash where if you say $ and then double parentheses, you can put it into what they call math mode. So I can say this thing is equal to itself plus 1, please. And here's the end of my loop. Great, so let's go ahead and we'll run this script real quick. And I'm going to start by running it on my local bin directory just to show you what it looks like. So I'll run out of sequence inodes on /bin, and I will pipe it to more. And you see the first one, the starting inode was 2, and inode 2 actually points to the root directory, so this makes sense. And then I have the rest of my inodes. So notice this is printed in red, telling me it's a big jump. Here, I was expecting 81 and I got 82, so it's printed in yellow. And then here you can see some bigger gaps. I can repeat this on my local sbin. I get some similar results. I can go ahead and mount my image, which is at Media, Fill, Toshiba, Disk Images, 2015 9. And that's been nicely mounted for me. I can rerun my script, and I'll run it on Media, Part 0, Bin. And again, I'll just pipe it to more. And as expected, the first sequence has a big jump, and then there's another big jump when I go to bash, and I see a big jump a little bit further down, but nothing too extreme. And there's a huge jump here for all of my suspicious programs related to my rootkit. So you can see that did a pretty good job of saying, hey, look at this. This is suspicious. I'll go ahead and rerun this real quick on sbin, and I will get some similar results. Great. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to go a little bit deeper into the wonderful world of inodes. Now,
Inodes, as we'll see, have a wealth of metadata. So this can be extremely useful to us as we try to examine a system and try to figure out what happened. So we're going to start with the simplest case, and that is with a standard inode that is 128 bytes long. And this is something you would find in an ext2 or ext3 system. Now, if you have an ext4 system, they will use 156 bytes, although their size on the disk is 256 bytes. And this allows for some future expansion. This way, if they add a couple of fields to the inode, you don't suddenly have to resize every file system to use the new features. So first of all, let's talk a little bit about finding an inode. How do I find where my inode lives? Well, the first thing I need to do is I need to figure out what is its block group. And to figure out the block group, all you need to do is take your inode number minus 1 and divide that by the number of inodes per group. It's pretty simple. Now, why do we subtract 1? We subtract 1 because inode 0 is undefined. We start our numbering at 1, and that makes the math a little bit weird, but if you want to see weird, you should deal with Microsoft file systems, and you'll see that they have all kinds of weirdness where sometimes things start with 1, sometimes 0, sometimes 2. So once you've figured out which group, then you need to know the index within that group in order to find the correct inode in the table. And that is just that same number, the inode number minus 1, modulus the inodes per group. So your offset into the inode table is then just that index times the inode size. Now, when I say the inode size, I mean its size on disk, not its actual size if there's some padding, as is the case with ext4. So what does this inode look like anyway? It has all kinds of information in there. It starts out with a file mode, then the user ID that owns it, its size, its access, change, and modify and delete times if it's been deleted, its group ID, its hard link count. We don't care about symbolic links here. We just need to know hard links so that when the last hard link's been removed, we can delete the file. How many blocks are used by this inode? Recall that the inode is everything you wanted to know about the file except for its name. Any kinds of flags. There's also several unions that are operating system dependent, and for the most part, you'll encounter ones with the Linux version. And if you were creating this file system with Linux, it would give you a version for your inode in that spot. And then you have the block pointers. There are 15 of these. They're each 4 bytes. We talked about these briefly before. We have the first 12 that point to data blocks directly, and then we have some indirect pointers as well. We'll talk more about those in detail later. Then we have the version. We also have the access control list if it's being used, the extended attributes, which are typically ACLs, but as we'll see, they can be other things. The file size, the upper 32 bits of the size, if it's an ext4 file system only. There's an obsolete fragment address, and then there is the second operating system dependent structure, In it, you see things such as the blocks, the upper 16 bits, file ACL, again, upper 16 bits, same thing with user ID and group ID. And then there's a checksum for your inode. Following that, we have the extra size. The extra size says, all right, a standard inode would have ended right now. So the first 2 bytes, we say how much additional storage is used in this inode. Then we have a checksum, and we have change, modify, and access times. And then here is something new. Now remember that only ext4 file systems might have these extra parts of an inode, but we have something that we haven't had before, and that something is a file create time. And then we have the create time extra bits as well. We'll talk about how to decode those in a future video. And then we have the version and unused space. So that's kind of our generic inode. Now there are a couple of special purpose inodes. First of all, inode 0, as we already said, does not exist. Inode 1 has a list of defective blocks. 2 is the root directory. 3 and 4 are user and group quotas. And 5 often contains the bootloader. 6, an undelete directory if it's being used. 7 is used for reserved group descriptors. Recall from some earlier discussions that you can reserve group descriptors for resizing a file system. 8 is something pretty important. It's the journal for a journaling file system, assuming it's not external. And then 9 is an exclude inode if you're doing snapshots. 10, replica inode. And 11 is typically the first non-reserved inode. And most often, what you will find there is the lost and found directory. So that's a lot of information. And we will, in future videos, we'll show you how you can get all this information out of the inodes. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, I wanted to show you a couple of ways that you can examine some of the wealth of information that is stored inside of an inode. So I wanted to first show you how you could do this using an image that you've mounted. So I'm going to go ahead and use our mount script. I see that it's been mounted under media part 0. I'll go ahead and change to that directory. And recall that we saw some strangeness in the bin directory. So I'm going to change to the bin directory, and I'm going to repeat my ls-ali r of my current directory, and I'm going to pipe that to sort-n for numeric, and I'll go ahead and pipe that to more. So again, notice that everything is nice and sequential. We also had a script that we showed you in a previous video that we can use that will point out wherever there are non-sequential inodes. And in particular interest to us were these last few files. So we can see here that these are nowhere close to sequential, so these were obviously added after the system was created. And the timestamps support that story. And in particular, we're interested in these files, the Xingxi files. So I can stat the file. So if I do a stat on Xingxi underscore star. This will print out information on each of these files. So here's the information that's coming right out of the inodes. What is the file size? How many blocks? Block size? What kind of file is it? What device is it stored on? What's the inode number? How many links? And who owns it? What are the permissions? And then we have some timestamps. Now, notice a couple of things. First of all, these timestamps have nanosecond accuracy. And we will talk about that in some future videos. So this is something that has been added to ext4, those extra bits that we briefly mentioned in some previous videos. And here you also notice there is a birth time. Now it's not populated in this case, but recall that we said in that extra bit that's in the new inodes for ext4 systems, there is a creation time now. And that's what it's reporting here. So that was pretty simple. I can look at the files and look at this information. I could also print out the files. I could cat the files. There are a few utilities that will also be useful to you that are built into the sleuth kit. So taking note of my inodes, 657,103, 076, 109. Those are the three that I'm interested in. Now I can use the sleuth kit. And we can start with istat. Istat will give you the same kind of information as stat for a mounted file, but this works with images and it also works with inode numbers. So I can say istat -o, my offset, then my image file, and then I give it my inode number, 657,103, and it tells me about this file. So notice it took a little bit of time, but it did eventually tell me the inode number, which is interesting since I supplied that. It's allocated, which group is it in, what's its generation ID. This is owned by user root, group root. Here's the mode, and it has extents in the file, and its size is so links. So here we have our times, and notice that we do have our nanosecond accuracy for all of our times, and then a list of blocks. You'll notice that these lists of blocks are contiguous. So we have 4 blocks, they're all in a row, and that is to be expected because it says they're using extents. If we look at some of the other files, here's its information. It's a little bit smaller. Once again, extents are being used, so we should expect contiguous blocks, and we have that once again. So here we can see when all of this was created, accessed, modified, etc. And then our final one here was also accessed earlier than it was modified, which seems a bit strange. And here's when it was created. It was created when it was accessed, which was before it was modified or the inode was modified. You can also print out these files, and the way to do that is to use icat. So I can use icat on one of these files. So let me go ahead and do that, and I have to supply all these options again. And I will pipe the results to XSD, and there you have it. So here is one of my files. If I repeat that but send it to more this time, you see right here that it says, I'm an L file, please run me. So either way, you can get the same kinds of information. You can either use the built-in utilities on your mounted image, or you can use the sleuth kit. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to have a little look at inodes. And we've talked about them before, and we kind of glossed over a few details. And now we're going to go back and tell you a little bit more about these things that we just sort of ignored before. And we'll start with file modes. So there is a 16-bit file mode vector, bunch of bits, and you're probably familiar with some of these already. So you know about the octal bits that we use for permissions. We can do chmod 777 if we're feeling lazy, which gives everybody execute, write, and read permissions. And then we have those permissions for our group, followed by those permissions for the owner, a sticky bit, a set group ID, and a set user ID. So these are all things that we can have. Now, all of these can be combined, so we can use whatever combination we want. In addition to this information, the inode also stores something about the type of file. And these in bold here are mutually exclusive. So you only get to pick one. So if bit 12 is set, you have a FIFO. If bit 13 by itself is set, this is a character device. If bit 14 is also set, then it's a block device. So notice here on bit 14, if it's all alone, it's the only bit set, this becomes a directory. But if bit 13 is set, as we said already, this is a block device. If bit 15 is set by itself, then this is a regular file. If 13 over here is also set, it's a symbolic link. And if 14, its next door neighbor, is set, it is a socket. So that's the file mode. Other things in the inode, we have flags. And we have lots of them. We have 32 bits of them. So if we look at the low word for the flags, we see here at first we have a secure deletion flag, which says if you delete this file, shred it, wipe it, don't just say the space is available. We have a preserve for undelete, so it's kind of an opposite flag. We have a flag to say this file is compressed. We have a synchronous writes flag. In other words, don't cache when you're writing to this file. We have a flag to say a file is immutable and should not be changed. We also have a flag that says, please only append to this file. Now, I should point out that many of these flags are here, but their support is non-existent. Not all of these things are supported by the operating systems. There's a no dump flag or a flag to say, please don't update the access time. Now, if you study Windows forensics, you will see that there is a similar flag for Windows directories. We have a dirty compressed file
We have a file with compressed clusters. And then we have a please don't compress this file flag. We have a flag that says this inode is encrypted. Another one for saying this directory has hash indices. We'll talk about what those mean in a future video. We can talk about AFS magic numbers. We can talk about data that has to be written through a journal. So you must use the journal when you write this data. We also can say this file, the tail of it cannot be merged. So you can't merge it together with something else. And that's only half of them. So what's in the other half? The other half contains things like this. The directory entry requires synchronous writes. So you can't cache the directory entry updates. This is the top of a directory structure. This is a huge file. This inode uses extents. We'll talk more about that in another video. It's fairly common. This inode stores large extended attributes. Typically, those extended attributes are ACLs, access control lists, but they can be other things as well. This is a deprecated flag that says there are blocks past the end of file marker in this file. There's an unused flag. There are a couple of flags related to snapshots. So here's one that says this is a snapshot. This one says the snapshot's being deleted. And this one says the snapshot shrink operation completed. There's also one for inline data. This can be useful when you have smaller files, and it can help speed up your I/O. There is also a reserved for ext4 library flag. Also in the inodes, we have timestamps. So in the lower 128 bytes, we have 4 timestamps: change, modify, access, and deleted. And these timestamps are stored in 32-bit values that are seconds since the epoch in 1970. Now, if we have an ext4 file system, typically on disk, the inodes are 256 bytes, and the current size of the actual inode is 156 bytes. So there's some room to grow, and there are extra timestamp values in the upper bytes. So what they do is the lowest 2 bits out of a 32-bit value are used to extend that timestamp to a 34-bit value. So currently the 32-bit values will overrun in about 2038. By extending it by 2 bits, it won't overrun past 2400 something. We'll all be dead by then, but who knows? Maybe our ancestors will still be running Linux and still doing forensics. The upper 30 bits are used to store the nanoseconds that should be added to the timestamp. So you now have nanosecond accuracy on these timestamps. So that's a little bit more detail on parts of the inode. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk about how we go from an inode to a file that it represents. So we're going to start out by talking about the inode block. So in the inode, we have a block, and often we'll hear people talk about this block, and they will say it is a block of 15 pointers. Now, it is more correct to say that it is 60 bytes of data. So what's in there? Well, if it's a regular file or a directory, you will have direct and indirect blocks sometimes.
The most generic case, that's what you have, but we'll see. You can have other things in there as well. Now, if you have a symbolic link and it is not very long, if you can store it in the 60 bytes, it's stored right in that spot. That way, you never have to leave the inode for a symlink. If it's inline data, there's a flag that is set in the flags, which we saw in a previous video. And then the first 60 bytes of the file can be stored in the inode. This allows you to store small files entirely within the inode. It can also speed up certain operations for longer files. Finally, if you have an ext4 file system, you can also have something called an extent tree. And we'll talk about what this means, but essentially it lists data runs or sets of contiguous blocks. So let's start with the simple case. In the simple case, these 60 bytes are used for 15 block pointers. The first 12 of these pointers point to data blocks. So if we have a standard 4K block size, this means I can have up to 48K in a file in these first 12 blocks. The 13th block is an indirect block, and what it has is a block that contains pointers to other blocks. So if I have a 4K block size and each pointer is 4 bytes, I can store 1K of pointers to 4K blocks. So this allows me to store a file that is as large as 4 megabytes plus 48K. So I can store quite a few files in that space. If that's not enough, in the 14th spot, I have a double indirect block that points to a block containing block pointers. So now I have 2 levels, and each level has 1K. So I have 1K times 1K of pointers, and again, they all point to 4K blocks. So this allows me to store up to 4 gigabytes plus 4 megabytes plus 48K using just this part of my block, using just this part of my inode block. The 15th block points to a triple indirect block that points to blocks containing double indirect blocks. So now I have 1K cubed times 4K that are stored in each of the blocks, or 4 terabytes. So I can have a file in theory as large as 4 terabytes plus 4 gigabytes plus 4 megabytes plus 48K. In reality, you can't really go quite that high, but who's got a file that large anyway, really? Okay, so let's talk about the new way of doing things. And this came about in ext4, and this is the use of extents. So what's an extent? It's a tree structure, and it contains 3 kinds of entries. It starts out with a header, and then you might have an index or a middle node in this tree. So it's not a leaf node, and it's not the top of the tree. It's an index or middle node. And then at the bottom, we have extents or leaf nodes. So each of these structures is 12 bytes long. The header we saw in a previous video in one of our examples contains a magic number, F30A, and then it has the number of entries that follow. After that, it has the maximum number of entries. In other words, how much space is there to store entries after this header? Then you have a depth. How deep does this tree go? If it's 0, this node points to data blocks, and if it's 1 through 5, this node points to other extents. Now, if you do the math, you'll find that you'll never need more than 5 levels. And then we have the tree generation that stored the version. The indexes, or middle nodes, are also 12 bytes. You have 4 bytes for a block. And that says this node covers this block and following. So what is this index for? It's for the following blocks. And then you will see a 48-bit value that's broken up by the lower 32 bits and then the upper 16 bits. And it has the block containing the node, the leaf, or another index that is 1 level lower in the tree. And that's pretty much all that's in the middle node. It just says, hey, here's the block that's covered by this node, and here's who's below me. I don't have anything terribly useful. I just point to somebody else. And finally, we have the extent node or leaf node. And it is, of course, 12 bytes long. And the first 4 bytes store the block that is first covered by this extent. And then we have a length. Now the length is encoded in an interesting way. If the number is less than 32K, that means there are this many initialized blocks in this extent. And if it's greater than 32K, whatever is stored there minus 32K is the number of uninitialized blocks. Then we have another 48-bit value, and we have the upper 16 bits of the starting block and the lower 32 bits of the starting block. So when we put all of these together, we can actually build our list of clusters. And it's stored in this tree structure. And we'll see some examples of that in future videos. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this short video, I wanted to show you how we can modify our Python scripts that we introduced in a previous video to account for extents. Now recall that extents are a new feature in the ext4 file system, and what we've done is we have added the ability to have file runs. These are something that if you're familiar with NTFS, you might have heard about these before, but the basic idea is we have a list of clusters, or in our case, data blocks that are contiguous, and they're stored in a tree structure. So what I have here is I've added a couple of teeny tiny classes. One of them is called extent header, and this is for that very first entry. And it tells you things like how deep is this extent tree. And if it's 0, which it most likely is, that means this is the bottom level. How many entries follow it? What's the maximum number of entries? Typically it's going to be 4, because that's how much you can store in the 60 bytes that you have. And I also made a pretty print function. I did something similar for the indexes. Those are those middle nodes, and they don't have much. They say, here's the block that this is for, and here is the 48-bit address for the block below me. Also made a pretty print. And then finally, I added a extent class that will print out the block. It has the length, how many data blocks are in this run, as well as the 48-bit address for the starting block. Once again, I defined a pretty print, and I added a simple method called getExtentTree that will take the whole 60-byte chunk. It knows that the first one must be a header. It will go through these and will add the header. And then depending on the depth from the header, if the depth was 0, then it's all leaf nodes and it adds them as extents. And if the depth was not 0, then it adds all the index nodes or middle nodes, if you will. So a small change here. If the extent flag has been set, then I will call getExtentTree and it will pass in my bytes. Otherwise, I populate this guy, this list that contains the blocks. Further down in my pretty print function, I've made a couple of simple additions here in order to pretty print the extents if they exist. And I also made it a little bit more user-friendly for some of these times. So it's pretty basic stuff, just a small extension. So what does it look like if we try to run this? So I'll go ahead and run my script. And now here's what I get. I have a listing that says I found an extent. It had a depth of 0 with 1 entry, a maximum of 4, a generation of 0. The generation is mostly unused, but it is a field that might be populated. And then we have, this is block 0, and here are the data blocks. This set, I can rerun my script on my other interesting inodes as well, and I see some very similar information. And that's pretty much it. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about going from inodes to file names. So how do we do that? Recall that the inode has all of the metadata. So what connects that metadata to a file name? Well, it's a directory entry. So what do these look like? If we look at the generic directory entry, it is something that maps names to the inodes, and each directory is treated as a file, which, if you know anything about Linux, should not be surprising because in Linux, everything's a file. So if we look at a directory entry, it starts out with an inode. Here's our tie-in to the inodes. And then we have a record link and a name link. And then we have the name. Now the name can be up to 255 characters. Now because of this record length being 2 bytes long is a bit wasteful. So what has been done in recent versions of the ext file system is that if you set a feature, you can have additional information in the inode. And in particular, we take part of that name length. Again, it can only be 255 bytes. And we use that extra byte that we were wasting before for a file type. So we have a file type of unknown, just a regular file, directory, character device, block device, FIFO, socket, or symlink. And these should look familiar. We've talked about these in previous videos and how this is in the mode information that is stored in some of these entries. And then we have our name string. So that's a small change. Now, another thing that you'll see in directory entries, we will install a directory tail. Now, what's this directory tail? It's a phony entry at the end of each directory block, and it adds checksums to the directories. So why is it a phony directory? We fake it out in order to have older systems that are not aware of these things not die or malfunction. So how do we do that? The first thing we do is we set the inode to 0. Because 0 is an invalid inode, legacy systems will ignore it. They'll ignore everything that comes after it. We set the record length correctly to be 12, and the name length is set to 0 because there is no name. We set the file type to a special value of DE. We then store a 4-byte checksum. So if you do the math here, there's 4 plus 4, and these three add up to 4 bytes. That's 12 bytes. Some other things that have been added. Hash directories. Why do you want these? Well, why do you hash anything? Those of us in security, of course, have reasons for hashing things. But general computer scientists will use hashes in order to improve performance. So if you have an older system and you're not using hashes for your directories, you have to do a linear search through the directories, which might take a while if you have lots of files. So here again, we fool the old systems by storing hash entries after the end of the directory block. We start an entry with a 0, and it says, oh, I must be at the end. Then we have our directory nodes in a hashed balance tree, or sometimes called an H tree. That's just shorthand for hashed B tree. And the ext4 index flag has to be set if your inode contains a directory H tree. Now, if you have hashes that are stored for your directory, you will still have their traditional dot and dot dot entries stored without the hashes. So these are not part of that whole system, and this is meant to speed things up. So what does a hash directory look like? You have your root hash directory block. It starts out, as we said, with your dot and your dot dot, and these are 12-byte entries. So we have our traditional 12-byte directory entries, and then we have an inode number set to 0 to fake it out. We have a hash version, and we have 6 different choices. You can see those here. We also have hash info length. We'll talk a little bit more about that, but that is traditionally set to 8. If you look at the length, how deep does this tree go? There's a flags entry, which is currently unused. There's a limit, the maximum number of entries that follow this header. There's a count for the actual number of entries. We also have the block. What is the block within the directory that corresponds to the first entry? And then we have entries. So the remainder of the block is 8-byte entries, and that matches our hash info length. So what does this look like? So that was the root directory entry. What about the interior directory entries? They also start out with the fake entry that points to inode 0, and they have a record length set equal to the block size. Traditionally 4K, the length is set to 0, and the file type is also set to 0. Then we have the limit, the max entries that follow, the count, the actual entries that follow, and the block. Again, this is the block within the directory for the lowest hash value of the block. And then we have directory entries. Now, the reason that I have these values here in red is that depending on where you look, I found these entries, and other places I did not find these entries. So I think it might depend on the exact version of the file system that you're running as to whether or not these three guys are present. So something to keep in mind. And then finally, the hash directory entry itself is going to be 8 bytes. So we have 4 bytes for the hash value and then 4 bytes for the block within the directory of the next node. So this tells us where to go next if this doesn't match. Here we also have the very end, the tail. And in the end, we have a reserved 4 bytes set to 0, which will cause it to be ignored, followed by a checksum. So there you have it. That is how we map our inodes to file names. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to show you how you can cat out files or print out files based on their inode number. And what we're trying to accomplish here is we're actually working our way toward being able to do directory listings for files that are stored inside of an image and do some other things with the files. We learned about directories in a previous video, and now we're going to apply some of that and extend our Python scripts yet again in order to be able to cat out a file associated with an inode. So what are we doing? Well, we've added to our xfs py file. So here's our inode class, and I've added a couple of functions. So the first function I've added allows you to get a data block where you give it an image file name, an offset where your file system starts, and then a block number, and optionally your block size if you don't have a standard 4K block. I will then seek to the appropriate place and return your block. Another function will return a list of data blocks. If you're using extents, I will use extents to give you the list. And in the case of using extents, we talked about these in a previous video, it is the most common case that you have a single level of the tree. So I have a little bit of a short circuit in this because I have to access the disk in order to get the list of blocks. That's why I had to define a method to read a block in. So here I take an inode object, and I also take an image file name, offset, block size, again optionally. I will take this, I create an empty list for my data blocks, and I say, are we using extents? If we are, the extents member for the inode object will return true, which means this list is not empty. And then I check and say, is the depth 0? That's the most common. If it is, I have typically up to 4 entries, and I say for I in the range of 1 to the number of entries plus 1, please go ahead and read this information. So I have a starting point and I have a link. So I add to my starting block my link. Now you might object and you might say, but I really wanted to have the length -1. That's what I should be adding. And you would be correct. However, because the range in Python is not inclusive of this final member, it will range from SB to EB -1. It seemed kind of silly to subtract 1 here only to add it back in the next line, so I didn't bother. And here I will just append whatever is stored in these extents into my list of data blocks. If in fact I have multiple levels to my tree, I have a pretty simple little while loop here, and I parse through the whole tree. And if you look at this code, what you'll see is that I'm checking to see, is this a leaf node? Is the level at 0 for this? Recall that every extent list starts with a header, and if the depth is 0, that means that everything that follows is a leaf node. So I parse the entire tree, and every time I find a leaf node, I add it. So I add it to my current level, and I start at 1, and I go to the end. And then I advance. I say current level is equal to my next level. So I'm loading this list. Now, once I'm done, I could do something really complicated where I say, okay, let's look at the logical block number, and we know that this one starts at 0 and then it's this length, so the next one should be here. Or I could do something super easy, which is what I chose, of course. I sorted my list, and that's what this construct does here. I said, I want to sort this. My sorting key equals lambda x dot block. So this says, please sort this based on the block. And then I will go through my list. I will do something very similar to what I did for the simple case. I have a little for loop, and I append all the data blocks to my list. Otherwise, I have old school blocks. Recall that the first 12 blocks are what we call direct blocks. I add those to my list. If I have more than 12 blocks, I have indirect blocks. I read in the indirect blocks, and then I iterate over those pointers. And since it takes 4 bytes per pointer, my block size, which is normally 4K, divided by 4, determines how many entries I have. So for each entry, I get the 32-bit value at the offset I times 4, and I say, is it 0? If it's 0, I call break, which gets me out of this for loop. Otherwise, I append it to my list. And I do something similar for the double indirect blocks. I've just added another level for my for loops. And once again, I do something very similar for my triply indirect blocks if I have some extremely large files. And it will go through this and add all of these block numbers to my list. And that's pretty much that. I've defined a new program called icat.py. What does it do? It takes an image file, an offset, and an inode number, and it displays the file for that inode. What I do is somewhat similar to my istat program. I create an extended metadata object. I find my inode. I load that inode into an object. Then I get my block list from that inode and image. argv1 is my image file. argv2 is my offset. And using the superblock size from my extended metadata object. And for each data block in my list, I call sysstandardOutWrite. So I cat it to the screen, and that's pretty much it. And I use my standard trick, if double underscore name, double underscore equals equals, double underscore main, double underscore, then I call main. So let's go ahead and run this real quick. So I will run it, and here I'm going to run it on inode 2, which you might recall is the root directory. I'm going to pipe it to xxd and pipe that to more. So here is my directory. You'll notice certain things that look familiar, such as lost and found, etc., etc. In a future video, we will decode all of this. I can also print out some inodes associated with my rootkit. Recall that this was one of them, 657,103. I pipe it to xxd and then pipe that to more. When I do so, I get something like this. It's an ELF file, and I will see some embedded strings. And this is, in fact, my rootkit. You can see Xing Shi and other telltale strings. Well, that's all for this video. As always, if you're enjoying these videos here at Pentester Academy, please tell a friend. Hello, everyone, and welcome to Linux Forensics here at Pentester Academy. In this video, we're going to talk a little bit about how you can use some Python scripts and build just a little bit more on some of the things that we've done already in order to read directories from their inode number. So the record starts out with the inode, then the length of the record, which is normally at least 12 bytes, can be longer. The name length, how big is this name? Recall that this used to be 2 bytes long. However, it was dropped to 1 byte to add the file type into the directory entry, which was sort of a cheat. And then we have our file name, which can be anywhere from 0 to 255 characters long. We also defined a pretty print function that prints out the inode, file type, and file name. And I'm calling a little helper function here called print file type that takes this number, this 1 byte number from here, and translates it. So what does that little helper function look like? It's right here. Print file type, and it will say either unknown, regular, directory, character device, block device, FIFO, socket, or symbolic link. Currently, those are the only values that are defined. If there's something defined in the future, it'll come back and say, I'm unknown with this code. We then define a method called getDirectory. It takes data, which could be a block or several blocks long, depending on how big it is. We set done equal to false, initialize an empty list, and then we have a little counter. And we say, while we're not done, create a directory entry. And then I'm going to check and say, is the inode in that entry 0? Recall that if we set the inode equal to 0, that means that there are some of these hidden values, such as hash directories, etc., checksums, other things that are stored in there. And for our purposes, we really don't need to look at those. We just want to look at the directory entries themselves. Otherwise, if it's a legit entry, we append it to our list, and we add to our pointer the length of this record. If we've gone off the end, we break out of this while loop. Otherwise, we go back and we read another one, and so on. Then we return our list. So it's a pretty basic function. So we've created a new file, ilspy, and it's essentially a lister or ls utility for inodes. And here's our usage function. It says, please give me an image file, offset, and then the inode containing the directory. And I will display it for you. If you didn't give me enough stuff, I will yell at you with my usage. Otherwise, and this should look familiar by now, I'm going to read in my super block, and I'm going to use that in order to create an extended metadata object. Once I've done that, I get my inode location using information from my super block. I call get inode lock, and I calculate my offset using some other things that we've done in the past. I open the file and I seek to the appropriate location. So here's the offset that I calculated from up here, plus arg2 was my offset in 512 byte sectors. I read in my data, and I read in one inode. Then I create an inode object from that, and I use my getBlockList function. Then I loop through my block list and I pull in all of my blocks. And then I say my directory is just get directory on those blocks. It could be just one block depending on the size of your directory, or it could be many. And once I've done that, I will get names, file names from my directory, which is just a list of directory entries, and I'll call pretty print. I will run this on our old friend, the image from our test system, and I will run it on the root directory, which is stored in inode2. It's a standard place, and sure enough, there you have it. I've printed out the different entries. Most of them are directories, but there are a couple of symbolic links and other files as well. Notice that I have the traditional dot and dot dot entries at the very top, and they both point to inode2, which in this case is the root directory. It's the top of the pile, after all. Also notice that lost and found is pointing to inode-11, which is another standard place. So if I wanted to look further, perhaps I want to look at etc, I could just take this inode number and I could rerun my script. For that inode, and boom, there you have it. And I could have modified my script. You're certainly welcome to do this if this is what you would prefer, in order to recurse through subdirectories. I just chose not to do so for this simple case. Primarily, I just wanted to show you how you could use some Python scripts in order to load these directory entries from an inode. A couple of quick things that you can do with a script. If I rerun this for my root directory, like so, I can examine some of these subdirectories, and just for grins, let's have a look at this temp directory, which is stored in this inode. So I'm going to go ahead and clear my screen, rerun my command for this directory, and what do you know? Sure enough, I see two files that are stored in my temp directory. Now in this case, these files were not stored as hidden files. They very easily could have been. And notice that these are a process ID and a port for my Xingxi Quan rootkit. So we can see we've added just a little bit more evidence to our pile when we were looking at what exactly happened in this case. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to talk a little bit about inodes and extended attributes. I know it's been a long journey. We've been talking an awful lot about inodes because inodes are just a wealth of information. So we're nearing the end at our investigation of the almighty inode. And today I wanted to tell you a little bit about extended attributes. Now, these are things that can be stored in the extra space between inodes. Recall that with ext4, typically on disk, an inode is 256 bytes. However, the current inode size is 156 bytes. So that gives you an extra 100 bytes. You can also store these extended attributes inside of a regular data block. You just have to point an element in the inode called file ACL to the data block. Why is it called that? The reason it's called that is the first use of extended attributes was in fact for ACLs, access control lists. However, you need to realize you can use this to store almost anything as a user attribute. As long as the name starts with user, period, you are fine. You can store all kinds of stuff. So some of you might be familiar with Windows alternate data streams, and this is a way that you can hide information inside of a Windows file. So you can do something very similar here in Linux with an extended attribute. We'll show you how to do this in a little bit. So if ACLs are used, the file system has to be mounted with the correct options if you have older kernels. If you have an updated kernel, this is no longer an issue. So it's just something to keep in mind. Probably won't come up for most of you, but it is a possibility. So if you're having some issues and you're running something that's not one of the latest kernels, you might want to look into that. What do these structures look like that are used to store extended attributes? Well, they start out with a header. Now, depending on whether or not this header is stored in an inode or in a data block, it looks different. So here at the top, I have what it looks like if you're storing it in just an inode. You have nothing but the magic number that's 4 bytes long. If it's in a data block, you have the magic number, a reference count, and the blocks used to store the extended attributes, a hash value, a checksum, and then there is some reserved space, 12 bytes of it. Following that, we have our actual entries. So they start out with a name length and then a name index. So what's this name index all about? This name index says, do I have a prefix? It would be extremely inefficient if I had common prefixes stored in ASCII or Unicode inside of every single one of these, especially given that I only have 100 bytes if I'm going to do it inside of the inode itself. 0 means there is no prefix. That user prefix that I mentioned earlier is 1. 2 means that you're using a ACL access list. 3 is another ACL access, in this case ACL default. 4 trusted, 6 security, 7 system, and 8 system rich ACL, which is not commonly used, but depending on the system, it might be used. Then we have the offset from the first inode entry or the start of this block. Then we have the disk block, where our value is stored, or 0 if it's in this block. The length of the value, and a hash for the attributes in block, or 0 if it's in the inode. The attribute name without a trailing null comes next. And that's pretty much it. So let's have a look at our extended attributes. So how can I look at these? It's pretty simple. There's a command get f_attr, and I can run it on a particular file. I can run it on all files. And if I run it in this directory, you see that I have nothing. As you might expect, there is a set file, setf_attr, and I can go ahead and set this on a particular file. Let's just set it on this one. Now, if I just hit enter, it's going to say, hey, you didn't give me any information. And it will give me a usage, like most well-behaved Linux commands. So I'll go ahead and say, oh, well, let me do this correctly. I want to give it a name, and my name will be user. Again, remember, I can get away with most anything that starts with user. And I'm going to say secret. And -v, a value. My value will be Mr. Roboto. That's my secret. I'm Mr. Roboto. Now, sure enough, if I run get f_attr, once again, it shows up and it says, hey, look, you have an extended attribute on this file, but I want to see what it is. If I run get f_attr, again, without any options or path, it says, well, what did you want to get? I want to do get f_attr -n, and the name I want is user secret, and I'll just run that on all of my files. And it tells me for most of them, sorry, they don't have this attribute, but sure enough, for this file, it says it has the attribute and it's set to Mr. Roboto. So this is another way that someone could hide some data on you. Similarly, there are get_f_acl commands and set_f_acl commands. So I can go ahead and say, tell me about that same file. And it tells me about itself. And it says, here's the file, here's who owns it. And it's got the standard permissions, nothing special. I can call set_f_acl as well. I won't actually do that here. That is something that you can do, by the way, in any Linux system that supports this. You know, perhaps you want to set some permissions for a certain user and you don't want to mess with the normal file modes. It's just a one-off kind of thing. You don't want to add someone to a group or anything like that. And this is something that you can do with access control lists. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon. Hello, everyone, and welcome to Linux Forensics here at Pen Tester Academy. In this video, we're going to wrap up our discussion of file system forensics by talking about extended attributes and showing you a little bit of Python that we can use in order to get extended attributes out of our image files. So here I've created a simple little Python program where I import all the usual things. I have a usage function, and I expect an image file, the offset to the start of your file system, and an inode number.
I do the standard thing. I first will open the image file. I will create an extended metadata object. I will get the location of the inode using stuff that's stored in the superblock and in the group descriptors. From there, I will go ahead and read in the appropriate inode. I used our good old friend with open, the recommended construct for Python, and then I create an inode object. And I figure out, does this have extended attributes? We'll see we've extended this inode class just slightly. And if it does, I'm going to look at the block number for the extended attributes. If it's set equal to 0, that means these extended attributes are stored in the empty space between this inode and the next inode. Recall that the inodes are currently 156 bytes long if it's an ext4 file system, and pretty much that's what we're talking about right now. If you're looking at older file systems, they don't support this. You have 100 bytes from the 156 byte where the inode ended to the 256 byte on disk where the next one starts. So if this block is set to 0, it's stored there, and I will get the extended attributes from my inode, and I will pass all the standard information that I need. This should point to the start of the extended attributes right after the inode is done. And this method says, oops, it's actually stored in an external block, which is also supported. So this method will get it from there, and then I use a for loop in order to print out the attributes that I found. If there weren't any, I just say there weren't any, sorry. We'll have a look now at our additions to our xfs py file. And I've added this method, get extended attributes in an inode with the appropriate parameters. I start out by defining an empty dictionary, and then I check the magic number. If that's not what I have, I'm going to short circuit and return my empty dictionary. Set done equal to false. Start my index 4 bytes in, because I'm skipping over this. And while I'm not done, I'm going to get an extended attribute entry, and I'm going to check and make sure it's not the end of the list. Then I will say, is this extended attribute stored in this block? Is it inline, if you will, or is it in an external block? If it's in an external block, I call get data block, and then I will get the information from there. A couple of little helper methods and classes. Here's my extended attribute entry class. Starts out with a name length, index, value offset, value block. Again, 0 means the current block, the size for the value, and also a hash. I give it a name. The name is going to be equal to the name that's stored, but with a prefix added. And we've talked about these prefixes in previous videos. So here we have a method to print these prefixes. And if it's 0 or greater than 8, which means I don't know what it is, I just return an empty string. Otherwise, I return one of these. So that is the method for getting extended attributes inside of an inode. The one for getting attributes stored in a data block is very similar. Let's go ahead and run this real quick.
I will run iGetAtterPy on an image with an offset of 2048. And I will look at one of my interesting inodes. Sure enough, it tells me it has no extended attributes. In fact, if you were to look through this file system, you would see that none of these have extended attributes. As a reminder, you can do the same thing using the tools. If you mount the file system, you can use getFadder and setFadder, which you wouldn't want to do if you're looking at another image. That wouldn't be good forensics, certainly. And you can look at it that way as well. But this is just another way, and I wanted to show you how you could modify our Python in order to do it with an image of a file system that's not currently mounted. Well, that's all for this video. As always, if you're enjoying these videos here at Pen Tester Academy, please tell a friend. We'll see you soon.